In this video, we're going to run through the extended response solutions to the practice SAC for the 2014 Module 5 Network SAC. Okay, so part 1, question 1. The following map shows the road between two towns, Argyll and Bonham. These towns are the major intersections for the vertices on the graph are labelled. The number of edges represent the road lengths in kilometres. Find the length of the shortest part from Argyll to Bonham. So we can see here we need to go from Argyll here to Bonham, just using the shortest path. So we need to consider what different pathways there are and check each of the possible paths and their lengths to work out which one is the shortest. So if we look going across the top, we can go from Argyll to C, E, G and down to Bonham, and that would give us a length of 1.8 kilometres. If we went from Argyll to C, D, F, H and across to Bonham, that would give us a length of 1.2 kilometres. If we went from Argyll to C, E, H, B, 1.3 kilometres. And we check each path and we work out that the shortest path is actually 1.2 kilometres. And we go from Argyll to C, D, F, H and then Bonham. And note, we do have to show all of the labels there, so you do have to say from Argyll and through. So question 2 then asks us, Argyll Primary School is planning a fundraising ride which covers all of the major roads between Argyll and Bonham. At present, it's not possible to ride along all roads from Argyll in the network and back to Argyll. Explain why this can be seen from the graph. So if we want to ride on every road and end up where we started from, that means we're looking for an Euler circuit. So if we look back at the graph, we can see that we have odd vertices. And so vertex C is odd and vertex G is odd. The rest are even. So that tells us we have an Euler path, but we can't actually make an Euler circuit. So in order to answer the questions here, we would say the reason why we cannot do the circuit at present is there are two odd vertices, and we would say where they are located, so at C and G, and therefore we cannot complete an Euler path, an Euler circuit. Obviously you'll write that in more detail in your response. So part B, by adding a road, will it be possible to complete the circuit? Between which two intersections should the road run? So obviously whenever we're trying to turn a graph into one where it is possible to have an Euler circuit, if there are two odd vertices, these are the vertices between which we add the extra edge. So we're going to add our extra road between C and G. Part C then asks us to list the vertices on a circuit that covers every road, including the additional road that we've just added in, so including that road from C to G. And we want to start and end at Argyll. Now there's various answers for this, and so it's just a matter of testing your answer to see whether it actually does cover each road just once. I'd recommend you using a highlighter or something with a bit of colour so that you can actually see whether you've traced over those roads or not. Okay, so question 3 then says, the day before the ride, Carly and Natasha are scheduling some last-minute preparations. The activities they hope to get through are listed on the table below. And we have our table of time and predecessors for each activity. Complete the network diagram below for the schedule above by adding in the required dummy edge. So here they're telling us we need a dummy edge. Now remember, in order to tell where the dummy edge should go, by looking at our predecessors, we're looking for any doubling up of activity where the actual doubling up doesn't match. So what I mean by that, here we've got a doubling up of A. A is a predecessor for two different activities, but in both cases A is the only predecessor there. If we were to look down here, we've got a G as a predecessor for H and a G also a predecessor for J. but J also has I as a predecessor. So G is doubling up, but the predecessors don't match for the two activities. So what that tells us is that we want to start our dummy edge from activity G, and then we actually want to, so the end of activity G, and it needs to connect into the start of this one here where there is a mismatch, so into the start of J. So from the end of G, we have our dummy edge coming around and joining in here at the start of J. Now, we traditionally draw that with a dotted line. We do need to label it. I tend to just use a lowercase d to represent a dummy. And remember, it has a weight of 0, so we put that there as well when we come back to it later. Okay, so part B then asks us to identify the critical path and the shortest time it will take to complete the day's preparation. So in order to do that, we need to do our forward and backward scan so we can identify our critical path. Okay, so I've just made that a little bit bigger and added our boxes so we can start our forward scan. So always starting at 0 at the start, we run along up to A. We have a 30 there as our earliest start time. Across to D, we have another 30, so 60 is our earliest start time. And down to F, we've got two paths to consider there, E and F. So at present, F would give us a time of 2:40. Let's go back and finish the other path. So from 0 along B, we have two paths there. B would give us 30, C would give us 60. So 60 in the box, 60 plus 60, so E would give us 120. And so 240 in the box. Across to G, so plus another 30, we have 270. Up to H, another 60, so 330. Now when we get to I, we have the dummy edge coming in, so we have to consider the path from the dummy, which would give us 270. And from I as well, which would give us 480. So 480 in our box there. And so 480 plus 30 gives us 510, 510 plus 30, 540 as our overall completion. And so doing our backward scan, start with the same number, so 540 in the box, minus 30 gives us 510, 510 minus 30, 480. Working down I, so minus the 150, 330 here. Now back here we have to consider the dummy and also H. So H would give us our 270. And the dummy coming back would be 480 minus 0, so 480, smallest number in the box, so 270. So you can see the dummy, in this case, doesn't have any impact on the critical path. Working backwards from there, 270 minus 30, 240. Up along F, 240 minus 180 will give us 60. 60 minus 30, now here we have to consider D and C coming back in, so D will give us 30. We'll go and complete the rest. So back down at the 240 minus 60 gives us 180. And back to the beginning, again, two paths, so A and B to consider. B would give us 150. And working from 180 minus 30 of C gives 150 again, smallest in the box, so 30 there, and 30 minus 30A would give us 0. So now we can see that our critical path will travel along from the start along A. So along A, D gave us that 30, so along D, down through to F, across to G. It was the H that gave us the 270, so along this way until we get to J, and then J and K to the end. So our critical path in this case is A, D, F, G, H, I, J and K, and that was a total of 540 minutes to complete the whole project. Okay, so part 2, we now have a country town with the streets represented in the network below. The numbers on the edges refer to the lengths of the streets in metres, and the letters refer to the intersections of roads. The two dotted lines without endpoints at A and F refer to the roads in and out of the town. So the shortest route through the town from A to F follows the main highway. Through which intersections does the highway pass, and what is the length of the highway passing through the town? So we need to work out where is the shortest path from A to F. So looking at our graph here, we again, similar to the first question, we need to consider all possible paths, but we're only going our shortest route from A to F. So if we were to go through B across to E and down to F, we'd have a total of 1,400. If we were to go from A through C down to D and across to F, we end up with a total of 1,100, and that's actually our shortest path. So the answer there, through which intersections does it pass? Well, it goes through A, C, D and F, and that gave us a total of 1,100 metres. Part B then asks us about some Shire engineers are passing through the town and need to examine all intersections in the town. They need to arrive in town at A before leaving at F to travel on to the next town. To save time, they want to pass through each intersection only once. So we're looking at Hamilton paths here, going from A to F. So the question asks us then to state the 4 routes through the networks of roads that would enable the engineers to achieve this. Now at this point it only asks for what the 4 paths are, but part 2 asks us the shortest of the 4. So I'm going to work out the distances as we go. So one possible pathway would be to start at A, go through B, down to C, D, up to E and down to F, and that would give us a total of 1,700 metres. A second possible route would be from A to C, up to B, back down to D, E and then F, and that would be 1,650 metres. A third route from A to C, up to B, across to E, back down to D and across to F, and that would be 2,200 metres. And finally a fourth possible route would be A through to C, then D, up to B, across to E, down to F, and that would give us 1,700 metres. So our answer here for our 4 possible routes were just the 4 that we gave, which were A, B, C, D, E, F. And remember that gave us a total of 1,700 metres. A, C, B, D, E, F, and that gave us 1,650. A, C, B, E, D, F, that gave us 2,200. And finally A, C, D, B, E, F, and that gave us 1,750. So the shortest route is route 2 that we've got there, so A, C, B, D, E, F, giving us a total of 1,650 metres as the total distance. Okay, now question 2. The gas company is installing natural gas pipes along each street. The gas company engineers chose to follow an Euler path through the network of the streets, ignoring the roads in and out of town. The main gas pipes come into the town at C and leave at E. So firstly we need to complete the Euler path. So we've given you the start there, and it's just a matter of following through the Euler path. So we actually end up with a path from C, B to A, C, D, B, E, and then D, then F and E finally. So part B, how would the gas company benefit by choosing an Euler path? Well, clearly an Euler path will cover every street, and it will only cover each street once. So when they're installing their pipelines, it means that they don't have to double up on each street, and it means that there's a continuous flow throughout that network. So that would be an advantage of using an Euler path. Okay, so question 3 now says an electricity company wants to install new lights at each intersection with the power cables being placed underground. In order to keep costs to a minimum, the length of the power cable should be a minimum. So if the substation is located at intersection D, show on the diagram where the cable should be laid. So what we're actually looking for here is a minimum spanning tree. Now remember, with your minimum spanning trees, there's a couple of different methods to actually get the minimum. But firstly, let's have a look. We've got a total of 6 vertices, so we know we're only going to need 5 edges. The way I do it is start with your smallest edge first. So we can see we've got a 200 between C and D, so I'm going to use that edge there. The next smallest number is 250, and so I'm going to join C to B and A to C there. Now the next smallest number is 300, but if I was to use that edge, I'm actually not helping out with my minimum spanning tree because I'm creating a little circuit there between C, B and D. So I discount the 300 and I look for the next smallest number, which is 400. So I can use this 400 here between E and F. Again, I wouldn't use the one between A and B because A and B are already connected in. The only connection I now need to make is this section at E and F into the rest of the graph. And so I look for the smallest edge that would enable that, and it's the edge between D and E, the 450. So there's my minimum spanning tree. And for part B, what is the minimum length of cable required? Well, I'm just adding those values together. So I'll do 250 plus 250 plus 200 plus 450 plus 400, and I end up with a total of 1,550 metres. Okay, so part 2. Steve has 5 volunteers who are capable of doing various tasks involved in the tournament. The following bipartite graph illustrates the tasks that each volunteer is able to do. So for instance, reading here, Paolo can be the catering coordinator or he can organise the equipment, but he can't drive the bus, do first aid or timekeep. So each of those arrows represent what each person can do. So allocate one task to each of the volunteers by completing the table. So we can already see Paolo has been given catering coordinator, which means he no longer is one of the people who could be the equipment manager. And we can see there that Denise has also been allocated to equipment. Now, if Paolo is the catering coordinator, that means Rex can't be the catering coordinator. So his only other job is bus driver. So that means Rex will be our bus driver. If Rex is the bus driver, that means Gina cannot be bus driver. And Gina's two other options were equipment and timekeeper. Equipment's been taken, so that means Gina has to be the timekeeper. And finally, the last job left is first aid, and we just check that Stuart can complete that. And yes, Stuart's the only person who can do our first aid. So that job goes to him. Okay, so question 3 then says the result of most of the matches over the 5 weeks has been shown on the graph below, where an arrow going from B to A would represent that Ballarat defeated the team from Ararat. So our dominance matrix for this graph is given on the next page, even though it says to the right here. And where a 1 represents a win and a 0 represents a defeat. So there was obviously a winner and a loser in every round of this soccer tournament. So the final matches, Ararat defeating Edenhope, Ballarat defeated Derranellum, Foxhowl defeated Colac. They are missing from the graph and we need to add them in. So it's just a matter of drawing an arrow from A to E to represent Ararat beating Edenhope and making sure we put the arrow in the correct direction. Ballarat to Derranellum, so B down to D. And Foxhowl to Colac, so across the middle there, Foxhowl to Colac, and our arrow going in that direction. We can now then fill in on the next page our adjacency matrix. And so if we flick across there, we're asked to fill in A to F. So from our graph we can see A to F, the arrow is going in that direction, so we would put in a 1 there. And C to C. Now there's no loops because in a tournament we can't play ourselves, so there's going to be a 0 at that C to C. So we'll just enter those values in there, our 1 and our 0. Part C, use the information given to find the team that did not have a 2-step dominance over the team from Ararat. Okay, so you've got the option here of either entering this 1-step dominance graph, so this is our 1 step up the top here, of entering that into your calculator and finding our 2-step by doing our 1 step. So if we call that x, just for the sake of knowing what we're talking about, our 2-step will be x squared. And then we can read from the Ararat team, we're reading down the column to check who has any 2-step dominances over that. So when we actually do that, we find that the only team that does not have any value or has a 0 in that first column is D, and that's Derranellum. So because it's asking for the town, we don't want to write just D, we do have to write the actual name. So you need to refer back to the context of the question. Part D, use the 1 and 2-step dominance matrices to find the overall winner of the tournament. So that means we want to do our 1-step plus our 2-step to get our answer. And so if we were to do that on our calculator, we would find our 1 and 2-step dominance matrices. When we work that out, we end up with a big matrix like this. And so from this combined 1 and 2-step dominance matrix, to work out the overall dominance, we're going to add the values in each row. So that means to work out the dominance of our rat, I'm going to add these values together. And for Ballarat, and so on. So working out the values across the rows there. So I'm going to represent that here just as a column matrix. So we'll put each team in. Now Ararat has, when we add that up, a total of 7. Ballarat has 9, Colac has 10, Derranellum has 6, Edenhope 8, and Foxhowl 11. So that tells us that the overall winner will be Foxhowl, and they have a total of 11 1 and 2-step wins there. Okay, so on to part 4. Hannah Enterprises is a firm contracted to design a new prototype of solar-powered vehicle. They have a warehouse located at W and a factory at F where the vehicles are constructed. So deliveries are made by trucks of the various sizes, and the loads change from one vehicle to another at points given along the way. At some points, more than one vehicle carries supplies. The diagram represents the changes in the vehicles along the way, and the numbers on the edges represent the maximum loads in tonnes that can be carried by that vehicle on any one day. So basically we need to know that the amount that can be carried along any particular pathway is equal to the value that's given there. So the first question asks, explain why the line labelled cut 1 above does not represent a valid cut. So we can see here cut 1 is cutting across these edges here. Now if we're talking about our warehouse to our factory as the direction of flow, so our start point is the warehouse and our end point is the factory, I can still get to the factory even with that cut. So that means that the cut 1 is not valid because it doesn't stop the flow from warehouse to factory. Part B then asks, find the capacity of the line labelled cut 2. So remember, when you're finding the capacity, you're adding the edges that get cut off, or where the flow stops. So working from the beginning, along this edge, I get cut off, so I add the 3. I can still get to the 5, which gets cut off, so I would add that value. I can still get to the 9 here, so I add that value. And along the bottom, I can still get to the 7, so I add that value. And so with that cut, I add those values together, so 3 plus 5 plus 9 plus 7, and I get a total of 24 there for that cut. So part C then says, hence or otherwise state the maximum flow of the warehouse to the factory. So when I'm doing my maximum flow, I already know at this point that 24 is a bit of a baseline. So I need to get my minimum cut and see if I can get a value smaller than that. So looking at my graph here, if I was to cut way up at the warehouse, I get a value of 9. So I already know that's smaller than the 24 from part B. If I was to cut at the factory, which is our end point, I would get a value of 4 plus 7, so 11. I don't add the 8 because it's going in the opposite direction. So at the moment, 9 is my lowest value. So can I see anything smaller than that? If I was to cut through my graph this way, I would add the 6 because it's going from warehouse. I would add the 2 because I can get to there, it gets cut off. But the 8 is not counted because I can't get through to the factory side to come out of that edge. So that actually gives me a weight of 8. And that is my minimum value. So the answer for part C is, what's the maximum flow? Well, it's 8 tonnes. Okay, so part 2 of this one. The company employed to set up the website for Hannah Enterprises has partitioned the job into 4 tasks and 4 contractors to quote for the price of each task. The contractors' quotes are in thousands of dollars. Now this is important, and this is a key mistake that a lot of people made in this SAC last year. So please note that for the end. So the contractors' quotes are in thousands of dollars on each of the tasks given in the table below. So part A, use the Hungarian algorithm to allocate one task to each of the contractors so that the total cost is a minimum. So we've given you tables, and I've said there, tables have been provided, but only use as many as you need. So don't feel that you have to use all 3 of those tables if you can arrive at an allocation prior to that. Okay, so I have to use the Hungarian algorithm, so let's start by doing my row reduction. So the smallest value in the first row there would be 20, so I'm going to subtract 20 from that row. The second one is 25. Third row, the smallest value is 30, and the fourth row, smallest value is 20. So when we do those subtractions, we end up with the following values in our table. So 0, 180, 40, and 100 in row 1. 0, 215, 40, and 75 in row 2. 0, 220, 40, and 80 in the third row, and then 0, 220, 30 and 70 in the final row. And so now I need to subtract the smallest number in each column because I don't have 0 in every row and column. Obviously the first one won't change. The second one I'm going to subtract 180 from everything there. The third one I'll subtract 30, and the final column I'll subtract 70. So I end up with these values. So I have a 0, I have 35, 40 and 40, 10, 10, 10 and 0, and 30, 5, 10 and 0. So at this point I want to test with my lines. So I need to cross out the zeros using the minimum number of lines possible. So down the first column will be nice and easy. I'm going to go across this bottom row here, and I'm going to cross out that 0 there. Now I've only used 3 lines for to allocate 4 tasks, so I need to move on with my process and go a bit further. Okay, so of the uncovered numbers, I look for the minimum, and that is a 5. So I'm going to subtract 5 from everything left uncovered in that table, which means I rewrite the values under the lines because they won't change. So I just rewrite those in to begin with, 40 and 40 under there, 0 and 0, and then I subtract 5 from everything that's left. So that will leave me with 5, 5, 5, 25, 0 and 5. And so now I check with my lines again. So I this time need 4 lines to actually cross out all of the zeros. So that means I'm ready to allocate. So if we look at where our zeros are, obviously task 3, the only person that's allocated to that would be Delia. And if Delia is doing task 3, that means she can't do task 4 or 1, which means Barry is the only person left that could do task 4. If he's doing that, he can't do task 1. The only task left for Charlie is task 1, and the only person who can do task 2 is Aaron. So we get our 4 allocations there. So in our answer at the bottom, we need to put in who did each task. So task 1 was Charlie, task 2 was Aaron, task 3 Delia, and task 4 Barry. And obviously you'll write their full names there. And the minimum cost, that means we go back to our initial table and we work out the cost for each worker doing each of those tasks. And so we would have 200 plus 100 plus 30 plus 50, and that gives us a total of 380. But remember, these are in thousands, so the answer is actually $380,000 in total. Okay, so question 3. Hannah Enterprises has identified 7 activities that must be completed in order to construct their prototype for a solar car. These activities and the durations in the table below. So the project network has been incomplete. Complete the network by adding the activities E and F to the diagram. Okay, so using the information above, we need to add in E and F. So we can see E has a predecessor of B, so it's going to leave from vertex B. Then we can also see that E is a predecessor for F. Okay. The other thing as well is F has a predecessor of C and E, and then becomes itself a predecessor to G. So let's draw that edge in. So that means E has to run from this vertex here, so that would give us E, and it has a duration of 3, so we'll just pop that on there. And F runs from the end of E and C into the beginning of G, and that has a duration of 1. Okay, so now we need to complete a table of earliest start times and latest start times. And in order to do that, and then the following question as well, finding the overall minimum time, we need to do our forward and backward scan. Okay, so let's look at doing that now. We've just added our boxes and we'll start from the beginning. So always starting at 0 at the beginning. A there would give us a 3 in the box here. Going up along B would give us 3 plus 6 is 9. along to E, we have to consider two paths, C and E coming in there. So C would give us 3 plus 6, 9. E would give us 9 plus 3, 12. So 12 in the box. Following down F, we've got two paths there, D and F. So D would give us 3 plus 4, 7. F would give us 12 plus 1, 13. So 13 in our box there. And finally, 13 plus 2 gives us 15 at our finish time. Okay, so we can actually answer question C now. What is the minimum completion time? That's 15 weeks. But let's do our backward scan so that we can get the rest of our latest start time and information for the table. So 15 minus 2 would give us 13. Going across D, we have three paths coming back in here, B, C and D. D would give us 9. Going back to activity F, so 13 minus 1 would give us 12 here. And up to E, 12 minus 3 would give us 9. And so now, working down activity B would give us 3 here. C, 12 plus minus 6 would give us 6, so 3 in the box. And then 3 minus 3 gives us 0 back at the beginning. Okay, so now question B asks us firstly for the latest start time of activity C. Now it's important when we're looking at that, latest start time of activity C, so we're looking here where C begins, but we want the actual latest start time of C. And so it's not always the number that's in the box. Potentially it's the number on the outside. So that's why I always say you need to write that information there and you can answer any question. So in our table we should be putting for the latest start time of C, we should have 6. And from our graph as well, the earliest start time of E, so activity E, earliest of activity F, earliest start time there is 12. So back down in our table, we're going to have 12 there. And we already worked out that that would be 15 weeks is our minimum time for completion. Okay, so the critical path for this project. So going back to your graph, you can see that the critical path will work its way through from A to B, then E, F, and along G. And that gives us our critical path. Okay, so question 4. Hannah Enterprises finds that it might be possible to speed up some of the activities. However, this would result in increased costs. The table below shows which activities might be reduced in time and the cost per week of each reduction. So here we have, for instance, activity B will cost $5,000 per week that we reduce, and we can reduce by a maximum of 3 weeks. So if we were to reduce by 3 weeks, it would actually cost us $15,000. So remember, that's cost per week. Okay, so part A, determine the shortest time to complete a production of the prototype solo car under the new arrangement. In order to work that out, we want to do all reductions and then find out what the new minimum completion time is. So let's flick forward to the graph, and we need so here we need to redo our forward and backward scan with our new values in there. So I've altered those values to reflect the full possible reduction. Okay, so from A we have 0 through there to 3, and then moving up B, that would be 6 in the box. E would give us 8, but from path C, we'd have 3 plus 4 is 7, so 8 goes in the box. Moving down F, D would give us 5, F would give us 9, so 9 in the box, and then 9 plus 2, 11. So we can see our shortest time to complete with all of those reductions made is 11 weeks. Now, in order to work out what we actually should do, we need to consider what actually has an impact. And so in part B, it's saying Hannah Enterprises will receive $6,000 in funding for every week they finish before the original deadline. Is it worth their while? So is it worth their while spending the money to make these reductions, or will the bonus funding not match the amount they had to spend? So in order to get a completion time of 11 weeks, how much did we actually have to spend? So obviously we wanted to look at the activities on our critical path to begin with. And so that was our critical path there. And so reducing our 3 weeks there would be 3 times $5,000. Reducing E, we reduced that by 1 week only, and so that cost us $2,000. That cost us $2,000 for that reduction of 1 week. Here where we reduced C, we reduced it by the full 2 weeks. However, C gave us an early start time of 7. And remember, we only put the biggest number in the box, so we actually don't need to reduce it by 2. If we were to only reduce it by 1, so down to a total of 5 weeks, then we would still get 8 here at the earliest start time, which would mean that we could still put 8 in the box and there would be no consequence, no blowing out of that whole time frame. So we do need to reduce C, but we only want to do it by 1 week. So it will cost us $4,000 for that 1 week. If we weren't to reduce it at all and left C's duration as 6, that would mean here at this vertex, we would have C giving us a value of 9 weeks. And remember, the 9 has to go in the box because it's bigger than 8. So that will impact the overall time and actually blow it out to 12 weeks instead of 11. So we do need to reduce that C, but only by 1 week. So in total, that would be $15,000 plus another $2,000 plus another $4,000. So that would cost Hannah Enterprises a total of $21,000. By doing that though, they would save 4 weeks off the original, and so for $6,000 per week, that would give them a bonus of $24,000. So is it worth it? Yes, it is, because we are saving 4 weeks, which gives us $24,000. We are spending $21,000 to make it happen, so they make a profit of $3,000 in total. And that's how we arrive at that final answer. I hope that was helpful, guys. Please note, if you have any questions or if you need further explanation, just let us know on Schoology.